Okay, can you guys hear me through the microphone? The microphone has had a malfunction, so I've clipped it to my shirt with a bobby pin. So if it comes apart, please raise your hand if you can't hear me through the microphone anymore. I might not notice it until after you've noticed it. Okay, here we are. I stated Green's theorem last time. Green's theorem is the punchline. Okay, it was one of the punchlines. It's one of the main punchlines. It's the statement of the fundamental theorem of calculus for vector fields and domains in R2 and their boundaries, which are curves. So I'm just stating here, let's start with the statement of the flux form of Green's theorem to remind you. You do not necessarily have to write this down. You've written this down already. But the flux form it says that the flux through the boundary of the domain is the integral of the divergence, with respect to area. So this is the integral of the divergence with respect to the area element of the domain equals the flux through the boundary of the domain. The normal component is the flux through the boundary. Some notation, F is mi hat plus nj hat. The tangent vector is dr dt. The unit tangent is dr dt divided by the magnitude of dr dt, which we also call ds dt, its magnitude. And I said the following, I said it before, I'm going to say it again. N hat is fundamental in the sense that n hat is out. We always want out. If you choose the counterclockwise tangent vector, as I've chosen here, it's quite clearly the counterclockwise tangent, then n hat and t hat are related through t hat cross k hat equals n hat. So you write n hat is equal to t hat cross k hat. Just remember that. Just draw this picture and just do that cross product. The cross product you do by taking your fingers along the first vector, sweeping to the second vector, and your thumb will point along the resultant. Okay? T hat cross k hat is equal to n hat. So n hat, all you do now is take this crossed into k, and you have to remember your cross product relations. I cross k is negative j. J cross k is I. So this component crossed into k hat right here is negative j. That gives you this term right here. And then this component crossed into k hat gives you I, the I hat component. And of course, it's a unit vector. And so you have to divide by its magnitude. And its magnitude is dx dt quantity squared plus dy dt quantity squared square root, which is simply ds dt. These are r's. I apologize for my sloppy handwriting. OK? So the flux form of Green's theorem is written this way. But if you want it like in its gory detail, you want to substitute what f is in here. And we'll need this in a second when I prove this. F is mi hat plus nj hat. And so the divergence is dm, d Mary, with respect to x, plus d Nancy with respect to y. dm dx plus dn dy integrated with respect to a over the domain is equal to, well, you have to flesh this one out. This is going to be m I hat plus n j hat. That's what f is. Whatever the components of f are m and n. Dotted into this vector over here, which is dy dt I hat minus dx dt j hat. That's the numerator. Divided by ds dt multiplied by ds. So you can see, I'll just divide it by ds dt multiplied by ds. We'll take that extra step. And then the right-hand side becomes the integral of m dy dt minus n dx dt. And I'm going to do the full change of variables here. ds is going to be ds dt times dt, and all of that divided by ds dt. So you see the ds dt's cancel out. You've noticed this probably in your homework. Okay? I haven't emphasized it, but it's something that occurs repeatedly. So this is going to be m dy dt minus n dx dt. Okay, integrated with respect to t. This is the parametrized version of this, where the integral is done around the closed boundary. So this is the parametrized version of the flux form. Why is it parametrized? Because I'm integrating with respect to t, which is the parameter. Sometimes you'll formally see this as the integral of m dy minus n dx. I've just personally never been comfortable with manipulating it this way. If I have to write it in this more formal version, I'd rather have it in that version up there, the original version, which really gives me a sense of the geometry. Okay? This is the flux form. The circulation form is the following. The integral around the domain of the k-hat component of the curl of any vector field is equal to the integral around the boundary of the domain, which is that curve, same curve that we had up there, of f dot t hat ds. Now, the difference here is that you just have to be careful with counterclockwise, because you are choosing a t hat. Okay? And so this is the counterclockwise direction. And that is because you've chosen a direction associated with the curl. And so that keeps these two operations consistent. Okay? But let me plug in what the k-hat component of the curl is. If you recall, the k-hat component of the curl is dn dx minus dm dy. That's the right-hand side. And I have to, and of course, I apologize. I always drop my dAs. This is what an old man does after a while. He just kind of does that kind of stuff. Sorry. I've been doing it so many times. It's integrated with respect to the area element, the area integral that we learned in chapter 15, which is why we learned the integral in chapter 15, right? So you're integrating this with respect to A, and then you have to flesh out the right-hand side. Well, you just kind of look at it, and you're like, oh, OK. This is m dx dt plus n dy dt. That's it, right? You can probably skip a step at this point. So this is going to be m dx dt plus n dy dt times dt. And that's the circulation form of Green's theorem. And let me just write the flux form right beside it. d Mary dx plus dn dy dA. So these are the two forms. These are two other ways to look at Green's theorem. OK, I got rid of the dt's on the last line. But just look for a second and notice that really they're two manifestations of the same thing. OK, as written, they should kind of jump out at you that they're two manifestations of the same thing. Imagine in this integral, right, you just replaced m and n. You could do that. OK, what would it correspond to if you swapped m and n and a negative sign, swapped m and n, and you swapped a negative sign? That would be creating a different vector field, which is called G, which is everywhere perpendicular to f, right? Because you swap m and n and put a negative sign, G dot f is going to be 0. Check that out. Okay? So if you swapped m and n here, okay, and put a negative sign with a negative, let's say a negative n, so swap m, comma n, and put a minus in front of n. So that gives me the left-hand side. The m goes to the n, so it's going to be dm dx. And then the n goes to the m minus negative dn dy. That's that negative sign I asked you to put there. I swapped and put a negative. And I do the same thing, and I hope it works Is it going to work? I'm going to make a mistake, aren't I? Did I make a mistake? Choking, choking, choking. No, 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 no. It works. It works. Math works. Even I make these trivial mistakes once in a while. I know you never see it. It never happens in this class. But I do. OK, so you swap m and n. OK, you bring the n over there, dx, dt. And let me get rid of the dt's. And then I'm going to put a negative sign in front of the n, plus m dy. And what you see is that this is dm dx plus dn dy. And this is the integral around the closed curve of m dy minus n dx, which is exactly that thing right there. Why? These two forms of Green's theorem, right? This right-hand side is a vector field dotted into the outward component, and that's related to the divergence. This right-hand side over here is the vector field dotted into the alongward direction. By swapping n and m, I'm creating a perpendicular vector field, G. OK? So G dot tangent is like F dot normal, because T and N are perpendicular to one another. It works, and we're going to use this to prove one of the theorems if we can prove the other theorem. Yes? Perpendicularity, right? So really, in the end, let's move to this board over here. Let's imagine we had a vector field F is equal to mi hat plus nj hat. This is a vector field. So there's a vector at every point in space. And I'm going to create another vector field, G, okay, that I want it to be perpendicular to F. So how do you create a perpendicular vector field to F? Well, the dot product of G and F had better be 0. Well, if I put n over here and put a negative sign, and put m over here and put a positive sign, now take their dot product, F dot G is equal to negative mn, this dot this, plus mn, this dot this, and that's equal to 0 for any m and any n. So if you got a vector field and you want to create its perpendicular, just swap and put a negative. Now I could have put the negative here also, but then that would have just worked the negative through the whole problem. It still would have worked out. You would have had a different negative in the problem. It would have canceled. Things would have worked. Life would have been nice. Okay? So that's the relationship between the flux form and the circulation form of Green's theorem. And today I'm going to prove what I'm going to prove to you. I will prove the flux form of Green's theorem. And then you will see, oh, because of the perpendicularity argument, then the circulation form must be true. Maybe I'll have you prove the circulation form in some other context of relevance to your grade. Yes, I did say that. But I'll do that in a minute. OK, let me do that in a minute. Yes? There's some DAs, yeah. Old man drops the DAs. Remember that? Yeah, I still do that. I keep getting older, and they keep falling more. Yeah, this should be a DA. Thanks. It's a DA. Thank you. I appreciate that. Sorry if I confused anybody. By the way, you know, I always argue about dimensions. This has dimensions. M and n had better have the same dimensions because they're part of a vector field. This has dimensions m or n divided by length times length squared. So it's m times length. And this has units m times length, and this has units m times length. So dimensionally, they're consistent. And really, I can't overemphasize how important it is as you go forward to consider dimensions, OK? But I'd like to do an example right now, if that's OK with you all. Because I think it's a fun example. And since we're in California, we're in the West, which is really strange to me. I've only lived here for 12 years now. I'm an East person. So it's always interesting to think about the West. I think of the West and the cowboy movies and all that stuff. And I think about ranches. And I want to consider area. Consider area of a large piece of land. Okay? So someone is a rancher, and he or she would like to measure the area of their land. Maybe they have encircled a couple of mountains, or they've encircled a valley between mountains, and they're able to put a fence around that. Okay? And they know how to put a fence around that. But now they want to sell their land, and they sell their land by square footage, by area. Square meters, let's say, because we're in the modern era. By square meters, by area. And so we learned at the beginning of chapter 15 that area is really straightforward to measure. I talked about taking a piece of paper and cutting up into little pieces, measuring all the area of those little pieces, right? If you were to try to do that on your ranch, you'd go nuts, right? You would go nuts because how are you going to do all of this, right? How are you going to chop it into little pieces and do those area integrals that I've asked you to do? It's a little stressful, okay? You don't actually do the area integral to compute the area, okay? However, you have farm hands, and you can make them ride around the perimeter, okay? They're riding all day long. You got to go get your cows way out there. You can ride the perimeter, okay? And I claim that by carefully doing a couple of measurements and riding along the perimeter, you can calculate the area of your land, okay? And then when you see it geometrically, you'll be like, oh, that's easy, okay? So we're going to use Green's theorem to figure this out. We're going to use Green's theorem to figure this out right now. And then we're going to do a little geometry to show you how Green's theorem relates to the geometry. So maybe that'll help you understand what Green's theorem is all about. Okay. So area equals this is the definition, equals the double integral over the domain of the number 1 dA. No, I didn't lose my dA. Thank you, second row. It's there. Okay? Now, so if I could find a vector field whose divergence is 1, or let's say whose curl is 1, let's make its curl 1, then I could use the circulation form of Green's theorem to maybe relate this integral to a line integral. Okay? So consider f vector equals negative y I hat plus x j hat divided by 2. Divided by 2. The curl of f is equal to dn dx minus dm dy k hat. And dn dx is 1/2, and dm dy is negative 1/2. So this is just 1 k hat. What are the units of the curl of f? Well, f has units length, and curl has units 1 over whatever the original units were. So this is dimensionless. This is purely the number 1. So this is purely k hat. Okay. Now, moving on. If I were to substitute this, oh, actually, I can stay right here. Let me just substitute this into Green's theorem. I have the integral over the domain of the curl of f dotted into k hat integrated with respect to a is equal to the line integral of the circulation f dot t hat ds. Now you got to go counterclockwise, right, over the boundary. But this is good because it says, look, curl of f for this vector field is 1 k hat, and dotted into the k hat, that's 1. So for this particular f, this all turns into 1, and I have the integral of the number 1 with respect to a is equal to the integral of this vector field f dot t hat ds. Or put differently, the area is equal to this integral f dot t hat ds. So the cowpoke, your farmhand, has to do a line integral. Why? If the farmhand can do this line integral, you can compute the area of this domain. What is this line integral, everybody? Let's take a look at this line integral. It's actually super easy geometrically. So what's the area? Let's substitute f on the right-hand side. F is negative y I hat plus x j hat dotted into my tangent vector, my unit tangent, okay, which is dx dt I hat plus dy dt j hat divided by ds dt multiplied by ds dt, right? So this is going to be dx dt I hat plus dy dt j hat divided by ds dt multiplied by ds dt multiplied by dt. So I'm just going to write it like this with the dt. So the ds dt's kind of cancel out. Okay? Dimensionally, look, this has t over t. That cancels out. Length times length is going to be length squared. Yes, sir?
The F vector field should be divided by 2.
Thank you. Divided by 2. I appreciate that. Thank you. I forget that factor of 2 all the time. Okay. And you know, if you want to do our kind of squint and cancel idea, this is negative y I hat plus x j hat dotted into dx I hat plus dy j hat over 2. Okay? So now, what's the measurement you're going to ask your farmhand to do? Okay, let me draw our domain. This whole board is for the drawing now, okay? And there's a ranch house where you can have a big pole on the ranch house, okay? A big pole so you can see it from far away. So let me put the ranch house. This is almost too. I don't want it to be that. It works for anyone, but my drawing starts to get sloppy if it's. Okay. Let me put the ranch house right here. Okay. It'll be the O ranch, so that will be labeled O. Also for origin. Okay? Now what do? You are right here. So you are right here. Here's your assistant walking the perimeter. The assistant walks in the tangent direction from here to here. The assistant is able to measure the straight line distance to there. How do you do that? Well, it's done with little telescopes mounted on a tripod, right? And you have to use a little bit of either you use parallax or you use a couple of angles to figure this out, okay? Maybe you have 2 things over here and you can measure, you know their distance here, and that'll give you the angle from here to here will give you the distance, okay? So let's say you have a way of measuring this distance, okay? Now, when you walk in this direction, you know your direction, and this is, you're taking a step which is delta x comma delta y. Delta x comma delta y. Okay? Now, superimposed on this whole framework, and I'm going to go back down here, superimposed on this whole framework is the following. I'm going to pull the 1/2 out. I'm going to integrate this is simply the distance, right? Is that distance, okay? So let me write that distance, which you can measure, multiplied by, look at this vector field. It's going to be negative y I hat plus x j hat over the square root of x squared plus y squared, dotted into dx I hat plus dy j hat. This vector, what is this vector? That is a vector field whose magnitude is 1. It's a unit vector field, and it's always pointing in the around and round and round direction. Okay? This is the vector field. So if this is a radially outward, so this is my origin, this is a vector field whose arrows are all the same length. It's like that old, the first basic vortex vector field that I gave you. But instead of increasing as you go away, all they tell you, they're all the same length, and what they're telling you is what's the direction to go around the origin. It just tells you what direction it is around. Okay? So this is the encircling direction. So I unfortunately chose this point over here, and maybe I should have chosen this point over here. So how's this distance here that you can measure? And you can measure your, this is your tangent vector, right? Which is dx I hat, delta x I hat plus delta y j hat. And over here, you have the around and round direction, which is this vector field. And there's the around and round direction. I'm going to evaluate it. Notice I'm making them so they're not parallel to each other. Okay? That's the around and round vector field. Okay? So this says you take the dot product of the around and round vector field with the amount that you walk, the vector field that you walk, that your horse goes. So maybe you go 20 feet. Okay? And so this is about 20 feet, and you take the dot product with around and round. What does that give you? Well, that gives you the component of this vector along the around and round direction. It gives you the component of this vector along the around and round direction. And it tells you how long, right? Because if this is 20 feet, this will be something less than 20 feet. And then you multiply it by this distance from here to here. This distance from here to here, which is that over there. And then you multiply it by a half. Where did that half come from? And that'll give you a piece of area. And then you do it again. You go here and you do it again. And you go here and you do it again. And that's an easy calculation for the cowboy to make. Because you know which way it is to the barn. And therefore, you know which way it is perpendicular to the barn, which is the around and round direction. If I know to the barn, I know perpendicular to the barn. And I know which way I'm walking. So I know the dot product of these two. I can easily calculate the dot product. And that's how you calculate the area. These are one measurement of distance and a couple of measurements of angle. Actually, it's really one measurement of angle because it's the relative angle. And you can always, the cowboy can always say how far he or she has walked with that horse. But what is this really doing, everybody? I want you to think about what this is doing. So let me zoom in on a piece of that. I'm not going to draw the whole domain. I'm just going to draw one element of that integral, right? So let me draw the origin here. And let me imagine, let's go straight out. OK, that's radially straight out. So you can measure this distance. And now you're walking like this. OK? You go from this point to this point. Does that make sense? So this is a point along the curve, and this is a point along the curve, approximately. And so now let me fill this in. The along direction, the perpendicular direction, that first vector field with the denominator of the square root, tells you what is the projection of this length. So this is going to be my delta x, delta y from here to here. We'll just do the top half of the triangle. Along this direction over here. So that's the perpendicular direction to away. If I wanted to calculate the area of this triangle, I would approximately say it's this length over here multiplied by this distance over here and divided by 2. And that's exactly what each piece of this integral does. The distance to the barn, the component of your base of the triangle that is perpendicular to the direction to the barn, divided by 2, and then added up as you walk all the way around. And that's how you actually survey an area. That's how you actually go about and do it. You walk around and you measure the triangle from me to there, and then from me to there, and then from me to there, and then from me to there. And I always create these little triangles, these little wedges. And it's those wedges that you're adding up, which is why you get the factor of 1/2. Okay? So I think that's a cute application of Green's theorem. It's cute because it is somewhat restricted. It applies to one vector field. But nonetheless, it gives you this geometric understanding. Okay? Any questions there? You all seemed riveted about that one. Yes, sir. L times d. L being the perpendicular length, right? I mean, maybe I should draw this a little more carefully. Let me draw this a little more carefully. The way you should think about this is you create a triangle whose base is d, the distance to the origin. You're right here. And then you as the cowboy are walking in this direction, okay? But this is to the origin. This is perpendicular. This direction is perpendicular. Right? So that vector field, that perpendicular vector field tells you which way this is. Okay? So if you project the dot product of this is delta x I hat plus delta y j hat. That's this vector right here. If you project that onto perpendicular, you get this. Okay? In this case, it's clearly delta y. Okay? And therefore, you are able to create this triangle right here. And what you're saying is the area of that patch of the domain is basically the area of this triangle. Of course, you're making a little bit of error, right? But we always do that error in calculus. We always make that error whenever we're doing integrals. That's the same area that you make when you do the Riemann sums. But in the limit of these things being very small, that error goes to 0. So it's the base. Now, we are sure that that's perpendicular. So it's the base times the height divided by 2. In this case, the base is this. I just called that L divided by 2. So that's what a survey does. That's when why people, that's why you see people with scopes surveying a plot of land. Because you're not going to get, you can only walk the perimeter. So you have to associate what's inside the domain with your walk of the perimeter. Okay? Yes? That's a really good question. I've never bought a mountain. All my, I don't know how they sell mountains nowadays, but it's a great question. Do contours count, right? Well, they count to true surface area of land. I mean, if you're going to farm, right, this area of land and it's at 45 degrees, you know that there's a heck of a lot more land if you had the same patch associated, right, that was flat, right? If the same footprint was flat versus at 45 degrees, you know for sure that the 45-degree one has more area. And so, vineyards, I'm sure they're going to care about the amount of total acreage, right, associated with the topography. And by the way, we're about to, when we get into 16.5 and 16.6, we're going to do area integrals over curved surfaces. So the extreme example is, I mean, just because I think your question is fun, I will digress. The extreme example is, imagine you had land whose footprint was a disk, right? But which was a mountain that was a hemisphere, a perfectly hemispherical mountain, right? Okay, well, we know the area of this disk, right? The area of this disk is pi r squared, wherever that radius is. And we know the surface area of this mountain, right? Which is 4/3 pi, it's 4 pi r squared. I apologize. It's 4 pi r squared, because that's the surface area of a sphere, divided by 2. So it's 2 pi r squared. So in this extreme case, the hemisphere is twice the area of the disk that cuts through it, right? So you better sell land by that. Or if you own it, you better do this. And if you want to buy it, you better do that. Try to convince them.
Surveyors counted the contours of the land.
Oh, I don't know what surveyors actually do when they count the land, but I'm sure they must count the contours of the land. They must count the contours of the land. And so if you come to think about that, if you kind of really press me on that, then you're going to be telling me that, I actually should be using Stokes' theorem. I'm using Green's theorem because I'm doing everything in 2D. But when we get to Stokes' theorem, you can actually count the contours of the land there. Yeah. So think about this with Stokes' theorem as we get to Stokes' theorem. Okay? That's good? Yes? Clarifying. Let me just clarify this point again. These are all manipulations of the right-hand side, right? They're all manipulations of the right-hand side. Okay? This is a vector in the tangent direction. This is you walk a delta x in the I hat direction and a delta y in the j hat direction. This tells you which way is perpendicular, the unit vector perpendicular to the ray to the origin. So it tells you the perpendiculars. Okay? Sometimes you're walking completely perpendicular, like in that drawing over there. Well, that line, no, it's gone now, okay? Here it looks like you're walking completely perpendicular, right? Here you're walking completely parallel, right? So in this case, when you're here, the dot product is 0. This dot product is 0. If you think about it, it creates an infinitesimally thin triangle because you're walking along the height of the triangle. Okay? So this is purely a direction vector. So I wanted to tease out the different pieces of it. So I don't expect, maybe this is confusing you a little bit, but hopefully it's not confusing you much, but I want to show you how each piece corresponds to something that's measurable, that's literally measurable. Okay? To the barn, perpendicular to the barn, the way I'm walking, and my distance to the barn. With those pieces of information, I can calculate the area of any domain. Yes?
Right there, where you just drew that, you go just to the left of that where it overlaps.
Right here?
Yeah, so the space behind, so because it doesn't pass the vertical line, yes, there's a segment that's kind of overlapped.
Yeah, so it doesn't, like over here? Yeah.
How would you measure that part?
So this is a good question, right? So let's make an extreme example of what you're suggesting. If I do this, right? And I'm saying you measure the triangles from here to here, and that gives me all this area, right? But if you think about what's happening here, right? So he's talking about this overlap. Right? If I turn this way and I'm measuring, I say, well, my process just measured the triangle of taking a step along the boundary and going to the origin, right? I heard it. Somebody said the word. Say it again. Say it loud. Didn't you say negative? Yeah, that was right. I wanted you to take credit for it. Yes. So the thing is, in this way, you're traversing it in this direction. And this way, you're traversing it in this direction. You get cancellation because the opposite directions. So you're going this way over here, and then you're going this way over here. You actually cancel out these areas. So by doing this process, you overcount some area, especially if it wraps around, right? Especially if I'm looking at the barn and my neighbor's land is crossing between my line of sight and the barn, okay? But then that will be picked up as you come around in the other direction. It's pretty. It really works out with the vectors really nicely. Yes?
Question I have, in the beginning, you said to consider the vector field. Does that, like, how would you know to use that specific vector field? Is it just with the geometry?
Well, okay, so how would you know? I told you.
Yeah.
But this is the first step in saying, like, okay, I gave you this basic vector field because it actually comes up a bunch in different types of applications, right? And no, this is the only vector field for which you can compute area. But that makes sense because you need a vector field whose derivative must be independent of distance, right? Because when you take its derivative, you have to have a 1 on the left-hand side of that divergence or the curl, okay? So this is the only vector field for which it would work. But you could also imagine, wait, professor taught me how to calculate centroid. Okay, what kind of I could actually use this process to calculate centroid. I wonder how I could use this process to calculate centroid. So now I can tell you where my land is centered. Okay? I'm not going to do that. That's a little more involved, but it's not that hard. And if you're studying and you want to think about that, actually you can do that. You would need a vector field that's quadratic in distance. So its derivative is linear. So the left-hand side gives you one of the terms of the centroid, the numerator of the centroid. And then you do a line integral around the boundary. Okay? I think this is not a contrived example. Like, I can make all sorts of contrived examples or just do some sort of simple calculus. This is actually really works, and it really has geometry, and it's really triangles. That's why I give you this example. I like it. Okay? Hi, everybody. That was my example of Green's theorem. We did a couple of examples. We did a couple calculations with Green's theorem. I'm going to do the proof of Green's theorem right now. Okay? I'm going to do the proof using the flux form of Green's theorem. Now, this essentially follows what's in the book. Okay? So it's only another 10 minutes. I may not get through the whole thing. Okay? But I want you to see this. Now, that doesn't necessarily mean you need to take notes, right? The notes you can follow in the book. You can Google it online and see the proof of Green's theorem. Every calc book has it. A little bit, I'd like to fill in these discussions with my own interpretation. So you can listen to my interpretation. I don't want you to lose my blah, blah, blah because you're scribbling too fast, OK? Because you can get it elsewhere. But I may actually ask you to do one of the proofs of Green's theorem or make the argument to prove Green's theorem on the exam, OK? I've been known to ask always the statements of the theorems, the definitions, and I have been known to ask a proof or two. And I don't mean like super rigorous proof. I mean, show me that you understand that the left-hand side plausibly equals the right-hand side. Okay? And the proof of Green's theorem is straightforward. Fubini's theorem. Fubini's theorem, Fubini's theorem. So let's do proof of Green's theorem in the flux form. I claim that if I can prove Green's theorem in the flux form, that little argument I made by switching with a negative sign automatically proves Green's theorem in the circulation form. Okay? So they're intimately related by that switch of m and n and the perpendicularity, effectively. And all I have to do is prove it in flux form. And here's the proof in flux form. The easiest way to start a proof is when you have to do an integral, start with a simple domain. See how it works out for this simple domain, and then work it out. And then make the domain more complicated, OK? So here we go. The flux form of Green's theorem is the double integral over a domain of dm dx plus dn dy dA is equal to the integral over the boundary of that domain of f dot n hat ds. So f in this case is m I hat plus n j hat. And n hat is right there, n hat. N hat is equal to dy dt I hat minus dx dt j hat. The domain I'm going to use is going to be a very simple rectangle for now. I'm going to go from y0 to y1. I'm going to go from x0 to x1. And that's my domain. That's D. I need to show you that at least for this simple domain, the left-hand side equals the right-hand side. And then I'm going to show you how you build it up for more complicated domains. Okay? So let's look at the left-hand side. Yes? Yes. It is divided by ds dt. That should be divided by ds dt. Sorry. Thank you. I jumped ahead of myself. Please divide that by ds dt. That. OK, what is the left-hand side? I'm going to split up the left-hand side. I'm going to do the x integral first here, because it's going to go from x0 to x1. Is that what I did? x0 to x1. And then do the y integral second, y0 to y1. dm dx. And this is a function of x and y, right? And so I'm going to do the x integral first is dx dy. Plus, I'm going to do the opposite for the second term. I'm going to do the y integral first, and then the x integral. And this is dn dy, which is a function of x and y, dx and dy. dy dx. Please find all my typos. That's good. Keeps you on your toes. OK. Fundamental theorem of calculus. The integral of the derivative is equal to the function evaluated at the upper bound which is m of x1 y minus m of x0 y, integrated with respect to y. Plus, fundamental theorem of calculus, the integral from x0 to x1 of n of x y1 minus n of x y0. And then I have to integrate this with respect to x. Well, this is promising to begin with. I just took the antiderivative, and this already looks like a line integral. These look like 4 different line integrals. Okay? So take a look at this first term over here. Let's take a look at this first term. This first term, I'm going to write the domain out again over here, and I say, oh, look at that. This first term says, go to x1, take the m component of f, and integrate it along dy. The second term, let's go to the first term over here. It says go to y1, take the n component of f, and integrate it along dx. Go to these other components, and this is take the negative m component at x0 and integrate it along dy. And this is take the negative n component along y0 and integrate it along dx. Let me label these. I'm going to call this 1. I'm going to call this 2. I'm going to call this 3. And I'm going to call this 4. That means this is 1. This is 2. This is 3. And this is 4. Okay? I want you to look at integral 1 just for a second. I'm kind of giving you the impressionistic thing, and I want to get done before the end of class. I want you to see how it fits together. What is integral 1? Let's do it right here. Integral 1 is equal to the integral from y0 to y1, from here to there, of m of x1 y dy. Well, what's the normal vector over here? What's the normal vector? It's I hat. The unit normal on this boundary is equal to I hat. M is equal to f dotted into I hat. Therefore, it is equal to f dotted into the unit normal on that boundary. The unit normal is j hat up here. The unit normal is negative I hat over here, which is going to account for that minus sign. And the unit normal over here is negative j hat, which is going to account for that minus sign. This term is simply the integral from y0 to y1 of f dot n hat along the curve x equals x1, which is along that curve. And then I have to integrate that with respect to y. Well, this is the s integral, right? Because dy along this curve is equal to ds, because dx is equal to 0. dx is equal to 0. It's just going along the y direction. So along that curve, dy and ds are the same thing. So I claim that this term, which is integral number 1, is the first term on the right-hand side. Is the term that goes up the square. And the signs work out too, because ds must always be positive. And in this case, dy is positive because you're going from a smaller y, y0, to a bigger y, y1. And so too is dx positive because dx is going from a smaller x to a bigger x. And the signs are accounted for the fact that the normals are in opposite directions on the boundaries. That's how it works out. That's it. It's that simple. It's fundamental theorem of calculus. It's that simple. Now, how do you deal with more complicated domains? How do you deal with more complicated domains? And it's actually it's also beautiful how to deal with more complicated domains. And what's the answer to that? Well, you build them up. you build them up. Okay? But let me build up a domain that consists of this kind of rectangle, the one we just had, and another rectangle that I've stuck on top of it. In fact, I will stick it like that. Because you realize that you can make really complicated domains by just tucking little rectangles into all of them, right? And you take a complicated jelly bean domain and chop it into little rectangles that fit as best you can. Look what happens here. I've effectively proven, conceptually proven over here, that Green's theorem, the flux form of Green's theorem is valid on this boundary right here. Okay? What I want to show is it's valid not on this boundary, but on the whole outer boundary by adding two pieces together. Well, by proving it's valid on boundary on domain A and separately on domain B, it's valid on domain A and separately on domain B, right? Which means as I go along the line integral of A, my unit normal is pointing out this way, like that, and I've shown that it's valid for this domain. And for B, it's valid where my unit normal is pointing out this way. So what happens is that you imagine the right-hand side is take the integral around the whole curve A, the flux through this whole curve A, plus the flux through this whole curve B, but the flux out of A equals the flux of A into B, whatever. The flux out of A equals the flux into B. The integral along this curve cancels out because the normals are opposite directions along this curve. But the function is the same because they're continuous functions. So what happens here is if you create any complicated domain, all their interior boundaries, all the contribution to the right-hand side of the interior boundaries all cancels out because of the opposite side of the normals. And then you can see, oh, he's starting to create a schematic of the jelly bean domain, an arbitrarily curvy domain. And that's how Green's theorem works. That's it. It involves a little bit of geometry, a little bit of understanding what your vectors are, and remembering Fubini's theorem and the fundamental theorem of calculus. If you can show that for the flux, you can show it for the circulation. I'm going to start doing surface areas on Friday, and I want to get to Stokes' theorem by next Wednesday. So please read ahead, and I will assign the homework, I promise you, as soon as I can.